For the first time in the US's history, the NASA osiris-rex mission was able to collect a pristine 4.5 billion year old sample from the surface of an asteroid. And in May 2021, the spacecraft set off on its 1.9 billion kilometer return trip to bring the asteroid dust and rocks back to Earth. 2 years and 4 months later, the sample return capsule re-entered Earth's atmosphere in September 2023, travelling at more than 44,000 kilometers per hour, marking an extraordinary achievement in space exploration. Like an ancient time capsule carrying materials from our early solar system, the sample from asteroid Bennu is allowing scientists to uncover evidence about the asteroid's origins from a possible water world and expand on the history of our solar system. What secrets have been revealed through Bennu's rocks and dust? How might this change our understanding of our solar system and the origins of life? And what's next for the OSIRIS spacecraft? I'm Alex McColgan and you're watching Astrum. Join me today as we recount the historic return of the sample capsule from the osiris-rex mission and delve into the fascinating things we've learned from it so far. In previous videos of osiris-rex, or origins, spectral interpretation, resource identification, and security regolith explorer, I talked about its launch back in September of 2016 and its incredible journey to the near-Earth asteroid known as Bennu. If you'd like to learn more about the mission, from breathtaking high-resolution images of the asteroid's surface to the moment of truth when, in October 2020, the spacecraft touched down and collected material from Bennu, I encourage you to explore my other videos. This video will focus on the return of the sample capsule and the project's findings. After 7 years of anticipation, space travel, and data and sample collection, OSIRIS-REx returned to Earth. Or rather, it passed by Earth in order to return its special cargo. As the spacecraft reached a point about 100,000 kilometers away from our planet, it jettisoned the sample return capsule towards the atmosphere on the 24th of September 2023. Then, OSIRIS-REx fired its thrusters to avoid itself colliding with Earth and began a new mission, which we'll talk about later. This calculated maneuver had to happen within a narrow window of time and at just the right angle in order for the return capsule to hit its target of about 600 square kilometers in a Utah desert in the western United States. That's roughly the size of the city of Chicago, or the size of the Isle of Man. As the capsule hurtled towards Earth at a top speed of 43,000 kilometers per hour, it became the second fastest human-made object to enter Earth's atmosphere, only 3,000 kilometers per hour slower than NASA's Stardust return capsule, and enduring an astounding 32 g-forces, or 32 times the acceleration due to Earth's gravity. To put this into context, standing on Earth you receive 1 g, and a typical person would lose consciousness with about 4 to 5 vertical g's. Today's astronauts experience about 3 g's during launch, and for very short periods of time, a fighter pilot may be able to withstand up to 8 or 9 g's with the help of a specialized suit and training to increase their tolerance. It's almost unfathomable to imagine the 32 g's the return capsule was built to withstand. The scalding hot capsule streaked through the atmosphere, reaching peak temperatures of around 2,700 degrees Celsius, which is about half as hot as the surface of the Sun, allowing ground-based infrared trackers to monitor its progress. Inside the capsule, the 120-gram sample from asteroid Bennu was protected from these extreme temperatures thanks to an advanced thermal protection system called PICA, or Phenolic Impregnated Carbon Ablator, which removed more than 99% of the kinetic energy of the vehicle and kept the sample below 75 degrees Celsius. PICA is a type of ablative heat shield which works by using a protective layer on the outside of a spacecraft to safeguard it during re-entry. Because the spacecraft experiences extreme friction on its way down through the atmosphere, it generates immense heat. As the temperature of the shield heats up, it burns away its outer layer in a process called ablation. During this process, the heat shield melts and vaporizes, and those gases carry the heat away from the spacecraft. This sacrificial shield prevents heat from reaching the interior of the return capsule, keeping the asteroid sample cool and safe. A couple of minutes after re-entry, the capsule decelerated enough to release the first of 2 parachutes, which helped to stabilize it for the remainder of its trip to the surface. About 16 kilometers from the ground, radars were able to lock onto the capsule's location and track it to within about 10 meters of where it would eventually land. And for the final 1.5 kilometers of descent, a second parachute was deployed to soften the landing to a leisurely speed of 18 kilometers per hour, or about the average speed of a cyclist on flat ground. From the moment it pierced Earth's atmosphere to when the capsule gently touched down in the rugged desert landscape of Utah, it took just 10 minutes. After years of planning, months of special training, and several rehearsals, the NASA recovery team moved in by helicopter to secure the return capsule and its contents. To ensure the sample was not exposed to Earth's environment, the capsule remained closed until after it had been moved to a clean room and decontaminated. But opening the sample canister didn't quite go according to plan. Within a couple of weeks, scientists at NASA's Johnson Space Center in Houston, Texas, were able to open the outer lid, revealing 70 grams of dark grey rocks and dust outside of the sample canister. While this bonus material from Bennu was able to be analysed and used in scientific research, it wasn't as pristine as the material held inside the inner sample canister. However, it would take months and the invention of a new tool before the curation team at the Johnson Space Center was able to open the main sample canister to reveal this pristine material. The mission was meticulously planned, so why did they need to invent a new tool just to open the canister? And why did it take so long? Well, for one thing, the bonus material slowed down the process of getting into the inner canister because all of that extra material had to be carefully removed, catalogued and stored. And while it may not sound like a lot, the 70 grams of the bonus material alone was 10 grams more than the mission's original target sample size. Another reason this took a long time is because all of these tedious tasks had to be done inside of a nitrogen purged glove box, an enclosed box with built-in gloves that is constantly flooded with a flow of neutral nitrogen gas to make sure the sample does not react with other gases in Earth's atmosphere like oxygen or water vapor. While use of this clean environment was necessary to make sure the sample remained uncontaminated, the glove box made a set of already tedious tasks even more difficult. But the main slowdown came during disassembly of the canister, called the touch and go sample acquisition mechanism, when 2 of the 35 fasteners holding it shut could not be removed with existing tools. The 2 problem screws had been infiltrated by dust from Bennu, essentially causing the threads to be stripped. Imagine having successfully retrieved this capsule after its arduous journey to Bennu and back, just to not be able to actually open it. But NASA engineers wouldn't be NASA engineers if they didn't immediately set to work to invent what was needed to crack this nut open. Because the samples needed to be protected from any contamination, the new screwdriver-like tool with custom fabricated bits made from a specific grade of surgical, non-magnetic stainless steel had to be designed, fabricated and tested before it could be introduced into the pristine glove box. But all of this time and effort paid off. 3.5 months after the return capsule touched down on Earth, the creation team was finally able to access the material inside the canister using these new tools. Another 51 grams of pristine Bennu material was revealed, and when combined with the bonus rocks and dust already collected, the total amounted to more than twice what the mission had aimed to bring back to Earth. The material was then catalogued and divided into smaller samples. At least 70% of the material will be preserved in its pristine condition for future generations to have the opportunity to study, and from the remaining material, more than 200 scientists at labs around the world will have the chance to study pieces of asteroid Bennu. So what's so special about this handful of space dirt? Well, just imagine being able to study a piece of our solar system's past, a sample packed with clues about the origins of life and the early solar system. What awesome stories could an ancient relic like Bennu tell? Just over a week after recovering the return capsule from osiris-rex, scientists got their first look at the bonus asteroid soil sample called regolith. While Bennu might have broken off from a much larger asteroid 1 or 2 billion years ago, its present-day chemistry and mineralogy were already set in stone, so to speak, more than 4.5 billion years ago. Since its composition has remained relatively unchanged, Bennu contains the primordial ingredients that were present before our planets existed. The sample from Bennu contains what are called presolar grains, which are microscopic crystals that condensed before our sun came to be. Depending on the composition of these presolar grains, we can get an idea for the types of stars that existed before our own solar system formed. The higher the mass of a star, the heavier elements it will be able to fuse together. For example, small and intermediate mass stars burn by fusing light elements like hydrogen into helium, and may eventually fuse heavier elements such as carbon and nitrogen. Large mass stars can fuse together even heavier elements like silicon and iron. Importantly, these large mass stars can end their life in a supernova explosion, creating elements even heavier than iron. Because these elements from stellar fusion get spread across the universe and recycled to form new stars, asteroids, and planets, we can learn about the ancient building blocks of our own solar system by looking at these presolar grains. A cosmochemist at the University of Arizona and member of the osiris-rex team said that initial analysis of these presolar grains showed evidence of small and medium-sized stars, but also of supernovae. This supports the idea that our solar system was enriched by a range of different sized stars long before our solar system formed. Initial analysis of the asteroid sample revealed a dust rich in carbon, nitrogen, and organic compounds. These ingredients are essential building blocks to life as we know it. NASA's osiris-rex science team also found evidence of water in Bennu's past, in the form of water-bearing clay minerals in the sample. These clay minerals confirmed what scientists had previously observed in spectroscopic surveys of Bennu, as we mentioned in a previous video. They indicated that Bennu may have originated from a larger body that once contained water. But how do these ingredients of life end up on a seemingly barren asteroid? And why is there evidence of water? As it turns out, these essential ingredients of life are abundant throughout the universe. Planetary scientists and astronomers have identified organic compounds across our solar system, throughout the Milky Way galaxy, and even in interstellar space. We find these compounds in asteroids and meteorites, on moons, in nebulae across the galaxy, and beyond. All it takes for these simple building blocks of life to form is a combination of oxygen, carbon, and nitrogen, which are the third, fourth, and fifth most abundant elements in the universe by number of atoms respectively. These elements are created inside of stars, and remnants from those ancient stars are spread across the universe. We are made of star stuff, and from what we've learned, the stuff of life is abundant. But the presence of amino acids and other organic compounds doesn't mean that life ever arose in those places. In fact, with no atmosphere and temperatures ranging from a frigid -73 degrees Celsius up to a scorching 116 degrees Celsius, Bennu is not a very hospitable place for life to have developed. Rather, the presence of organic compounds means the building blocks of life seem to be abundant throughout the universe, and asteroid Bennu is further proof. Astronomer Dr. Carl Sagan once compared the emergence of life to a musical composition. The organic compounds on Bennu are like a collection of unorganized musical notes that do not yet create the music itself. Still, finding these molecules in such a pristine sample from Bennu is exciting, as these minerals could offer clues about the chemical reactions that predate biology. More intriguingly, perhaps, is that planetary scientists like Sarah Russell at London's Natural History Museum and an osiris-rex team member said the sample is dominated by hydrated minerals, suggesting that Bennu may have once been part of a larger body that harbored water. The sample was packed with evidence of dynamic transformations that occurred over time in the presence of water, like clay minerals or salts left after water evaporates. It contained a mineral called serpentine, which mirrors a type of rock that we find at mid-ocean ridges on Earth. These mid-ocean ridges are where molten material rises up from within Earth's mantle and encounters water, creating new crust along the ocean floor. Bennu's regolith also harbored pyrrhotite, an iron sulfide material that can form near hydrothermal vents on Earth. And even more surprisingly, the osiris-rex team found phosphates in the sample, an essential component of DNA and, in turn, for life on Earth. The presence of these water-soluble phosphates indicates that billions of years ago, Bennu may have been part of a larger, water-soaked mud ball, or even a world with an active geology and an abundance of organic compounds. While there isn't enough evidence yet to conclude that Bennu came from an ancient water world, Harold Connolly, a geologist at Rowan University and osiris-rex mission sample scientist, said that evidence of warm water over time in the sample does indicate that Bennu's parent body was at least 10 kilometers wide or even larger. Although more research is happening in order to further study these indications, it's incredible to imagine that Bennu may have originated from a much larger asteroid or a protoplanet that shared some important characteristics with the primitive Earth, or with some of the icy, ocean-covered moons across the solar system like Enceladus or Europa. So what else can we learn from the Bennu samples, and what comes next for the osiris-rex spacecraft? The data and samples from osiris-rex will keep scientists busy for years to come, as planetary scientists, geologists, astrobiologists, chemists, and interdisciplinary research teams around the world continue to study this one-of-a-kind sample from Bennu. And while we have a pretty good understanding of how the solar system and our planets formed, this is giving us the opportunity to calibrate, confirm, and adjust our current knowledge, and to explore the answers to new questions that are only possible because of the osiris-rex mission. Did the stellar nebula of dust and gas that went to form our sun and planets all come from just one ancient star? Or did it come from multiple generations of stars of different star types? Where did Bennu's parent body form? And what materials was it made of? And during Earth's formation and early existence, did some of its water or organic compounds come from asteroids? These are just a few of the long list of questions that scientists are hoping to shed light on in the coming years with the help from the Bennu sample. As for the spacecraft's missions, they don't end there. About 20 minutes after releasing the Bennu sample capsule above Earth's atmosphere, the osiris-rex spacecraft fired its engines to send it on a new trajectory and a new mission. Now renamed the Osiris-Apophis Explorer, or Osiris-Apex, for its new target, the spacecraft will travel to and explore a different type of asteroid, this one named Apophis, and it will reach in 2029. Starting in June 2029, it will begin an 18-month campaign to map the asteroid's surface, analyze its chemical makeup, and to observe any changes that happen to Apophis during a near-Earth encounter. Finally, the spacecraft will repeat one of its most impressive maneuvers from the mission to Bennu by dipping within 16 feet of the asteroid's surface and firing its thrusters to stir up rocks and dust. Unlike with Bennu, the Osiris-Apex mission will not collect a sample from Apophis, but this move will give us a chance to look at the material that lies below the surface of another near-Earth asteroid. You might have also heard that asteroid Bennu has a chance of colliding with the Earth in 160 years, although this is a very slight possibility of less than 1 in 1,700, so we most likely have nothing to worry about. But in addition to the scientific investigations centered around the return sample, the osiris-rex mission to Bennu also gave scientists precision tracking information that will significantly reduce the uncertainties about Bennu's future orbit. The initial analysis of Bennu's samples have exceeded our expectations in several ways, and I can't wait to see what other secrets Bennu and Apophis will reveal. I've spoken a lot about asteroid Bennu in today's video, but there's one other meteorite I wanted to mention, the Huzian meteorite, which was formed 4.56 billion years ago, making it older than the Earth itself. This meteorite crashed down into what is now northern Scandinavia 1 million years BC. Its octahedrite form shattered on impact. Around 40 pieces are known of today and are held in various institutions around the world. It's one of the oldest known meteorites. Why do I mention this? Because fragments of this piece of space history with their fascinating Widmanstätten pattern iron structure can be yours, found embedded in Novium's Hoverpen Interstellar, the sponsor of today's video. I think that's very cool. Having a piece of meteorite makes for a really unique space gift, but the Hoverpen itself is classy, a high-end and innovative pen that won Time magazine's One of the Best Inventions of 2022 award. It hovers in its cradle thanks to its magnetic fields alone, no need for electricity. It's comfortable to write with, refillable, and comes in a variety of different colors for all tastes, in beautiful, ready-to-gift packaging. Black Friday is just around the corner, so if you're looking for an artistic desk piece inspired by space or a special gift for a friend, why not scan my QR code or click my link in the description below. Viewers who use my code Astrum at checkout get 10% off Novium products, along with free shipping to most countries. But during Black Friday, this rises to 20%, so don't miss out. Thanks for watching, and thanks to our crew of Astromnauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you haven't already, but you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.